Welcome to this class, and today we are gonna look at functions and limits, and we are going to be discussing some of the things that are going to make up functions and limits, and that will be useful in terms of economics to understand functions and limits. So more we will lean on the limits as we are going to go on. But then before that, let us start from here. So now we want to understand what a metric spaces are. So a metric space, is a set X on which is defined a measure of distance between the elements. So it's just a set X where there is a measure of distance between the set of between a set of elements. So in short, we are saying the set where we can measure distance of the elements, distance between those elements. So now here, there's this scenario where we're saying, think of income levels of households. So let's say there are two households that earn, one maybe earns 50,000. Let's say this is kwacha. Let's say 50,000 kwacha, and the other one earns 70,000 versus kwacha per month. So we have these two households. So now the measurable distance, or the distance between their income, when we subtract, that is the 70,000 minus the 50,000, we get that the distance between their income is just going to be equal to to 20,000. So that is what we are saying to be a metric space. It has to be measurable. So the space, or the gap that is between the 50,000 earning that is there and also the 70,000 per month is actually measurable. So that's what a metric space is. So now, why, or before we talk of the why it's important, maybe looking at some of the key properties that are here when it comes to to the distance, which we are saying, this measurable distance. So first of all, the distance must be positive. So it must be positive. The distance must be positive. And then also we are saying it must be symmetric. The distance must be symmetric. So what do we mean by symmetric? We mean that the distance should make sense. That if we say maybe we're talking of the distance that is from maybe A to B there, that it is measurable, and from or maybe you're talking from distance from B to B to A, like that. So it has to be It has to be symmetric. Okay, and also then the other one which we are saying is another property that is important for the distance is that it must be the shortest the shortest path. So the direct route, or the shortest route that you would take. So that is some of the properties about the distance. Now, why is this important, or why does it matter in when it comes to economics? So we're saying it's a measure of how close the value are to each other. So here this metric space is showing us how close these values are to each other. So now this here is the difference, or how showing us how far apart. So it's either how close or how far apart they are from each other. So it's going to be very important, because you measure, it will help us to reach maybe when it comes to prices, or when it comes to income, like here, we'll be able to know that the difference between one person is earning and the other person is this. And maybe you're trying to look at how we can be able to reduce that gap. Or maybe you are trying to look at how do these gaps affect the living of people. Maybe how, when it comes to how they are spending money, you want to look at these gaps. So they're going to they're going to help us. They also help us when it comes to building models, and when we want to involve convergence. So that is, maybe you are looking at the difference here. Does it go to a certain value? Let's say we had a lot of looking at a real life situation where people have different earnings, and maybe you want to see, like, does the difference between their earnings approach a certain value? for maybe certain households. Maybe those that earn maybe low incomes, does it go towards a certain value to say this is what the difference that is there amongst the top class people? So that is what the metric space is going to be helping us with. Okay, so next we are going to look at this part. And this part we're just talking about sequences. So a sequence is just an ordered list of what? Of numbers. So a sequence is just an ordered list of what? Of numbers. And then we are saying these numbers, we usually list them either from ascending order or what? Or descending order. We either list them from ascending or what? Descending. So there has to be a list that smoothness and not like a number. You have a bigger number than smaller, like it's so jumbled, but it has to be in an orderly orderly manner. That's the reason why we're saying it's an ordered list of numbers. So now, for example, here we have two examples saying we have the arithmetic versus arithmetic sequence. So this sequence is 3, 7, 11, and 15. And you see these dots here. So the dots just mean it continues to go up to what? Up to infinity, which we'll understand in a moment. So now here, when you look at each term, so each term in this sequence is increasing by what? By 4. Hence, we're calling it an arithmetic versus sequence because you're performing what? An arithmetic here that is just what? Addition. So you're adding here. So it means to the first term, you add 4, you get 7. To 7, you add 4, you get what? You get 11. To 11, you add 4, you get what? You get 15. So it means our next term after 15, when we add 4, has to be what? Has to be 19. So then the terms continue to go just like that. So that's what a sequence is. And then another example here, you have the square of numbers. So here the square of numbers, of which in our case is just given n to the power 2. So you see you have 4 there, you have 9, 16, and what? And 5. So which n, of course, n is taking up values starting from, in our case, it's starting at what? 2. So 2, 3, 4, all the way going up to what? Up to infinity is how this sequence would be. So this is 2, you put it there, you square it, it gives you what? The 4. Then you say the next number, which is 3 to the power 2, square it, it gives you 9. The next number, you square it, it gives you what? 16. And you square 5, you get 25. So meaning the next value here, if we replace 6 and square it, we're going to get what? 36. So that's the next term that would follow in the what? In the sequence. So now, these are just examples. Now, types of sequences, we're saying there's a finite sequence. So a finite sequence is just a sequence that ends at some point. Like here, it's just listed, you have 3, 6, 9, and what? And 12. 3, 6, 9, and 12. So even here, you would say you're just adding what? You're adding threes from the previous term. So you have 3 here, you add 3, you get 6, you add 3, you get 9, you add 3, you get what? 12. So then it ends where there at what? At that point 12. So because it ends, then it's a finite sequence. Then you have infinite sequences. These continue forever. They go up to Up to infinity. That's why we just indicate by the by those dots there. Okay, so how is this so relevant when it comes to what we are looking at today? So it shows us the time parts of of maybe incomes. So you can see that an income could be increasing. Maybe somebody's earning increases over a period of time. So very useful also when it comes to looking at time series analysis. This will be very useful. So let's say in the first year, you're annually making a 60,000 kwacha, and then you see after maybe a year, they increase that to to 70,000 kwacha, and then it's increased to 80,000 kwacha, just like that. So this here is showing us a time-based ending of of your income, where your income is is increasing annually, of course, by in this case, it's increasing by by 10,000. So again, since we are talking of increasing, meaning we are saying that it's going to be important because it shows us growth of of the process over time. It shows us the growth of of the process over time. So another example that we can take is an example of inflation. So you know that inflation is given by by a percentage. It can be 4%, 5%. So if this, let's say from the time we are saying we were in 2016, if our the inflation rate has been increasing from then by 1% each year, then you know that from the time that you started up to the time where you are, there has been a certain growth over that period. So these sequences are the ones that will help you to identify those growths that you're going to have. Well, if there's any question at any point, please feel free to ask. All right, so now we move on to look at the concept of a function. So I want us to first just kind of understand these, and then we'll later look into a few questions here and there. So functions, in simple terms, we're saying a function just shows us how one variable depends on another variable. Shows us how one variable depends on another variable. So meaning that in that function, you need to have an independent variable. So an exogenous variable. In the case which we usually denote by by x, it's independent, meaning it's not affected by by anything. And then you have the dependent variable, which is the endogenous, which is this one is dependent upon the value that the value that x is going to take up. So let me give an example. Let's say we have y is equal to x squared. So x squared here is defined for what? For all real numbers. It can take up all real numbers. So if I put 0 there, 0 squared, you're gonna get 0. So and then if I put 1, you get 1. If I put 2 there, square 2, you get what? You get 4. So you see that x is taking up values, that is x is taking up values these 0 1 2 like that, but then the outcomes here, those are the values of the values of y, and those are the dependent, or that makes y the dependent variable. So the value of y is dependent upon upon x, and so we usually denote y to be equal to the function like f of x, where you have to plug in plug in x for you to get the value of the value of y. So just in simple terms, that's what a function is, or that's what we're going to be looking at, or that's how we're going to take it. Now we are saying, what is a limit? So a limit is the value that a function approaches. So it was important to get this notation of the function that we put it here when it comes to limits. So we're saying a limit is a value that a function approaches as x gets closer to to some number, let's say a. So mathematically, we've written it like this. So the limit of this function f of x as x is approaching a is equal to is equal to L. So L being being the limit there. So what this means, if we draw, let's say graphically, we have this. And then let's say we have a function. We have a function. Okay, I'll just say it's a function like that. And then you have maybe this point here. Let's say this point is 2. So meaning that, let's say, and then this function is defined by maybe 4x squared, like that. It's defined by 4x squared. So it's y in short is equal to 4x squared. So what does this mean? So now when you're taking the limit, you're saying, as I am approaching this value 2, what am I getting? So the limit as x approaches 2 of the function that is 4x squared. What is this limit? Is what you're trying to to do. And then when we start evaluating, of course, you just understand that first of all, the first approach that you do is to plug in directly and see if it works. So if you plug in this here, you have like 4 and then 2 squared, which is just 4. 4 by 4, you get 16. So the limit there you have is what? The limit is what? Is 16. So it's just telling you, as you get closer to 2, as you get closer to 2, that is in the x-axis, then this function here is getting closer to what? Getting closer to 16. That's what the interpretation of the limit is. So now this idea is what is very important. It does not mean here where we have x is approaching a, that shows us that x does not necessarily mean that it has to be equal to what? Has to be equal to a. But we're saying it has to just be closer to to that point. Okay, now we bring in the issue of one-sided one-sided limits, which are going to be very useful when it comes to our understanding of limits. So we have the right-hand limit. So the right-hand limit is just telling me the value. So I draw this here. the xy plane like that. And then let's say I have, again, I'm saying 2, maybe there's a certain function here uh, that is there. Let me just draw, maybe, yeah, that, like that. Okay, so this is not necessary to mean that this is how it is, but I'm just drawing it that way. And then this now, the limit, the right-hand sided limit is telling you that as you approach x from values that are greater than what? That are greater than a. In this case, it will be 2. Then the limit is going to what? You have to check that limit. What is that limit going to be? So in short, as we approach from this side, from the right hand side going to where our value is, what is that limit? And then the left hand limit just tells you, as I'm approaching x from the left hand side, this side, from these limits that are less than a, what is that going to what is that limit going to be? So now for the limit to exist, so this you must take note, for the limit to exist, both the left sided limit, which is the limit as x approaches a from the values that are less than a, that is of f of x, should be equal to the limit as x approaches what? A from the positive, or from the values that are greater than what? That are greater than a. If this is equal, if they are equal, then the limit what? Does exist. If this is not equal, if it's not the case, then the limit does not what? Does not exist. So this is a very important what? Important rule to take note of. Okay, now speaking of rules to take note of, there are rules that these kind of limits what follow. And just summarize them to be this here, saying uh, the first one is the constant. When it comes to limit and when we're computing limits, we're saying when you take the limit of a constant, it's still going to be what? To be a constant. So the limit as x approaches a of, let's say the constant that is k, this still gives you what? Gives you k. So the limit, let's say the limit of, if I was saying x is approaching 2 of maybe a constant I have 4, this will still give me what? 4 is what this rule is telling us. Then for polynomial, if you're taking the limits of a polynomial, you substitute x equal to what? To 8. So what this means is in your function, the same way we did where we had the limit as x is approaching 2 of 4x squared. So this here is a polynomial. And then you just make that direct what? Substitution here. So meaning the limit here is going to be, you replace there 2 squared, and this gives you what? 16. And that is what that rule is telling us. And then they're telling us that we can actually distribute limits over addition and subtraction, multiplication, division, as long as the denominator is not equal to 0 and over powers. So what does this mean? So if I take the limit, the limit of x as we approach a of, let's say I'm having two functions, that is f of x plus f of what? Okay, plus g of what? G of x. Example of these two limits. I can distribute this limit to say the limit of x as we approach f of x plus the limit of x as we approach a, as the limit of g of x here as we approach what? A, like that. Okay, so you can distribute that, and the same with what? With subtraction. So if I put that there, you can distribute. And also with what? With multiplication, we can what? We can distribute there. So if you're multiplying two functions, you have the limit as x approaches a of f there and g there. So this here, you can just get the limit. This is equal to the limit as x approaches a of f of x, then multiplied by the limit of x as we approach of what? G of x. If you're able to separate your functions like that, then you would write it that way. Then also, we're saying when it comes to division, so if you say you have the limit as x approaches a, you have f of x there divided by g of what? G of x. So you can take the limit on top, limit of as we approach f of x there, of that function, I mean f of x as we approach a, divided by the limit of x as we approach a of what? G of x. As long as this g of x here is not gonna give you what? Is not going to give you 0 when you take the what? When you take the limit there. So that there should not get a 0 in the what? In the denominator, because we know that's gonna be undefined. All right, and over powers, the last point just says you can distribute over the power. So that here is just means if you have the limit x as we go to a of the function f of what is given like that, and then you have n there. So distribute over the power just means you can get the limit as we approach a, and then the function f of x like that. You get this limit, and then the power should be there. So you can do that. Okay, so this is some of the basic rules when it comes to limits. Okay, now we move on to a concept of continuity. Move on to the concept of continuity. So we're saying that a function is continuous if its graph one has no breakages. So if, let's say I have a graph that is just, it's smooth like that. There are no breakages in this what-is, then we know that it's what? It's going to be continuous. But then that's not the only point mathematically. But in our interpretation, that's what we're saying. If we have a smooth curve like that, it's going to be what? It's going to be continuous. If there are no jumps, no gaps, then it's going to be what? To be continuous. So like this function here, almost all polynomials are just got continuous, depending on what you're talking about, which you understand at the next one where we're saying you have continuity at a point. Then you have this one which would not be continuous, where let's say you have this from here to there, it's defined by that, and from there to there it jumps, and then it's defined like that. Yeah, so here this function has a jump or has a breakage, so it's not, wouldn't be what? Wouldn't be continuous. Now, continuity, okay. So why continuity matters is the smooth production of what of the function first of all is going to be very important. And then we are saying for reliable predictions and focus that we're going to have, we need to have smooth curves. Maybe also when it comes to having well-defined marginal cost and marginal products, continuity what plays a big role. Now, continuity for conditions for continuity when it comes to continuity at a point. That is here we're saying when x is equal to a. What are those conditions? So all these three conditions must be there, must hold if that function must be what? Must be continuous at that point. So that is, first of all, it must be defined that what at that point it must exist. So the limit, for example, as we take the limit of a as we approach maybe in the function, oh, let me use 2, the function this x squared. So first of all, it must what? This limit must what? Must exist. That is, when I plug in directly into this function, 2 squared like that equal to 4. This must exist. So I know this is going to be there on your graph, in your graph there. Y is equal to us, it is there, equal to what? Equal to 4. So at that point, it should be defined. It's what we mean. And then when you take the limit, it must what? Exist. The limit must what? Must exist as we approach what? As we approach 2. So as we approach 2, the limit must what? Must exist. So this means that the left-sided limit and the right-sided limit must what? Must exist. So if they exist, then you have that you're going to get the what? The same. If the left-sided limit and the right-sided limit exist, then the limit does exist. If they are equal, I mean, if they are equal, then the limit exists. So as we said, the limit as we approach a from the left side of the function, if it's equal to the limit as we approach from the right side, if these are equal, then the limit as we approach a of f of x what exists. Then the point which you've defined, first of all, you did check that, okay, it's defined at that point, and the limit what does exist. So the limit must equal to what you defined at that point. So if they are not equal, then it means that that function is not continuous at that point. That function is not continuous at that point. So, okay, these are just the basic rules that are there. And then when you get to look an example, you get to what to see what we mean. Okay, after saying that, it leads us to our example. But before we go to these examples, do I have any questions? Okay, so there's no question. Let us now go into our examples. So the first question here that we have, the question says evaluate the following what? The following limit. So it's the limit of this function, the function. So f of x is just equal to, in this case, 3x squared minus 5x, and then you have x plus what? 6. All right. So now the fact that you are dividing by something here. In short, you have a rational function. So if you have a rational function, what you don't want the denominator to be what? To be equal to 0. So first of all, you substitute. Let's see, you always go first, the easy method. The easy method is first substituting to see is it going to be defined at that point. So if I substitute 4 here where x is in the denominator, I'll have 4 plus what? Plus 6. And 4 plus 6 is equal to 10. So this here is not equal to 0, which means I can go ahead by doing this direct substitution, since I do not get a 0 there. So meaning the limit as x approaches 4 here of this function. Anyway, I don't need to write that again since it's already there. So I can just say this here is going to be equal to, so I replace it directly on top. I'm having 3, then there 4 squared minus 5, and then 4 there, and then we divide by 4 plus 6. This here is going to give me, I square there 4, I just get what? 16 there, and then you have 5 multiplied by what? By the 4, which gives us 20. So then you multiply that 16. I multiply my 16 by 3. So 3 by 16, I just get 48. Down there, I got 10. So that will be 48. Okay, 48 minus 20, which is over 10, which gives me 28 over what? Over 10. And this here is just 2.8. 2.8, or you can just simplify it by dividing by 2. So if you leave it as a fraction, you have 2 there on top, 28 divided by 2, you just get 14. Down there, divided by 2, you get 5. So you can leave it like this, or you can write it as 2.8 like that. So this is our answer. This is how we find the limit. Okay, next we have this question here. It's saying a country's GDP per capita over time is modeled by the sequence. So these examples are based on whatever we've looked at today. So modeled by the sequence, this. So the sequence also, I did forget to mention that a sequence can be given by a formula. You don't have to just have a list of numbers and just like that, but you can be given a formula that is generating what the sequence that you have. And also, I think from the one which we had in the example, the formula we had seen that was n what? It was n squared in that example which we had. Okay, but then for this sequence, we've been given that it is yn is equal to 50,000, and then you have 1 minus 1 over what? N. Okay, so where yn represents the what? The GDP per capita at time n, and n represents a unit of what? Of time. So a unit of time, like 1 unit of time.
You've written 5,000. Oh, okay, sir.
Okay. All right, then they're telling us to determine the long-term behavior of what? Of this sequence and its implication for economic what? Economic growth. So they have used the term here, determine the long-term behavior of what? Of this sequence. So in short, what they are saying is, as we approach infinity, if we take the limit of this function here, so this here is the what? Is the function. If we take the limit of this function, as we approach infinity. So in short, we're saying as n goes to what? Goes to infinity. Goes to infinity, what is this going to be giving us? So as n goes to infinity, notice that this 1 over n is going to be what? Approaching 0. So as we go to infinity, 1 over n is approaching to 0. Why? Because you see here, this 1 over n, if we keep on putting big values there, this 1 over n, if I continue to put big values, let's say I put 300 there, I punch in that, so that's 1 divided by 300. You look at the value on a calculator, you're going to get like 0.003333. So as as the value goes so big, it becomes that this here is going to be approaching what? 0. Because if I round off, let's say the same one who said this 1 over 300 to the nearest decimal point, you just have 0. So it approaches what? It approaches 0. And what does that then mean for us? So if we take the limit as we go to infinity, it means that this here, this function yn, is going to approach, we say 5,000. You have 1 minus what? That will go to 0. And then this here is going to be 5,000 what? Multiplied by the 1, which just gives us what? 5,000 there. So this tells us that we are approaching what? We're approaching 5,000 as we over a very what? A very long time. But then they also tell us what do these implications mean for our economic growth. So this then means that the GDP per capita increases over time. So that's the first thing. It's going to increase over what? Over time. Then also it's indicating that the growth slows down and converges to what? Converges to this 5,000. So the growth slows down. So as we are going, you no longer get what? Big numbers here. You no longer get any big numbers. But then we are saying that the growth is what is slowing down and is converging to a certain value. And that value is what? That 5,000 there. And also we're saying there's a steady what? There's a steady income here, steady income level, which is what? Which is 5,000. It means that you're going to have this income, no matter how long you're going to grow there, it's still going to what? To converge to what? To 5,000. Okay, is that a question?
Okay.
Yes.
What does the formula mean? Like the 5,000, like what does it imply?
Okay,
The 5,000.
you mean the answer or this part of the formula here?
Yes, the function. What does the function imply?
Okay, so if you heard me here, as we said at first, they're telling us first of all, it's representing what? It's a sequence. So what do sequences tell us about the certain function? It's a behavior, like over time. How is it going to be? So, for example, if we say this was being used, or it's being here, it's saying n represents a unit of time. N, it's been given in the question that n is representing what? A unit of time. And let me say, if the unit of time was, let's say, we are indicating by months. So it would mean that in month 1, maybe you're starting. Okay, let's say that we're not starting from month 1, we're starting from month starting from 2. That is n. Maybe n is taking up value starting from 2 going this way. So what would that mean? Notice how this function would be. So if you put 2 there and then you say 5,000, and then you say 1 minus 1 over 2. So this here subtract, you get half, like that. So half multiplied by this 5 what? With this 5,000. What is that going to give us? That is going to give you 2,000 what? 2,500. And then you increase this here. Let's say you increase it by 5. And then you have 1 minus 1 over what? Over 5 there. That gives you 4 over 5. And then you multiply that by 5,000. You're going to have what? 4,000. Oh, here I didn't write this well. Let me erase here. So the first one, notice we used what? We used what? We replaced n with what? With 2. Saying that we're starting, that's at 2 months. Then we got a value of 2,500. Then when we replaced 5, we got, this gives you what? This will give you 4,000. Replace another number, you see that it's going to increase, but then this increasing will stop at some point, and then it goes to what? To this 5,000. So meaning that your income becomes stable or fixed over time to be just what? 5,000. That is what this is telling us, that, okay, you have a series of incomes first that you'll be getting. In this case, this is the GDP per capita will be that, but then over time it's going to be what? To be kind of fixed. Yeah. So this is what this sequence or that function there is what is representing. I don't know if I've answered your question.
Thank you, sir.
Okay, yeah, welcome. Well, this class or this what is going to close in the next minute. So just rejoin using the same link that we continue and just finish up the questions. So the following now are these which we're going to answer this set. So this one is telling us find the limit of each of the following what function. So the first one is for this f of x being equal to 3x minus 1 as x is approaching what? 2. We find the limit as what x approaches 2. So what is that going to be as x approaches 2? So the first thing we said is, especially when you have these linear polynomials, whatever, and just replace it directly and see what you get. So if we replace 2 here, we're going to have 3 there, 2 minus 1. That is 6 minus 1, which is just 5. So the limit as x approaches 2 is 5. Okay, then next we have this here, which is f of x being equal to 4 over x. F of x being equal to 4 over x. So what is this limit going to be? So for this one, I'm gonna sketch because here we're approaching 0. So here you can't put 0 down because we don't want the denominator to be what? To be 0. So first of all, let us sketch and see a representation of this. So 1, it's not defined at 0. So we know it's not defined. So meaning let's start from values like 1. So if we start from 1 there, and we start there -1. So if I put in 1 where x is, you're going to have that you get the value of what? Of 4. Let's say 4 is there. So this will give us 4. And you put in -1, you get what? You get -4. So to be on the opposite end, this side, -4. You put -1 there. And then if you put 2, let's say 2 is there. Okay, so now here we're trying to just what? To plot this function to see how it looks. Okay, so first, also another approach that you would be saying is if you replace, then it doesn't work like that. The value approaching, it's good to sketch it to see what it's about. So here we're going to have, if it's 2, we plug in 2 there, you're going to get 2. So let's say 2 is there, you're going to get that value of 2 somewhere there. You plug in -2 there, you're going to have, this will give you what? -2, which is there. Excuse me. So like that, plug in 3, you just keep on getting numbers that are going to be less than there. And they are here, they'll be approaching like that. So you basically have a line like that, and you have another line there like that. I know it's not the most accurate sketch, but yeah, that's what this here is what is telling us about. Then, now, as you approach 0, here, what are we going to do? We'll take the limit as x approaches 0. First of all, start from the right side of f of x. So f of x is what? Is this same function, which is this which we've sketched. So in short, as you are going this side, as you're approaching 0, 0 is there, right? Like this. Where is this function going? So you see the values that it's giving you. They're going towards positives, positive, like they're increasing. It's increasing and then increasing in the y, like that. You have y positive values that you're going to do what to be getting as you get closer to what? To 0. So it's going to, this here, the limit is just positive what? Infinity. Then when you're approaching from the left side of 0, there, the values you're going to be getting of y, you see there, those values are what? Are reducing. So they're going towards what? Negative what? Infinity. So the left-sided limit, so let me erase here. The left-sided limit is going to be, you have the left-sided limit, x approaches 0 from the left, of f of x is just equal to what? Negative infinity. So in short, the limit of x as we approach from the 0 from the positive of 4 over x is, of course, not equal to the limit of 0 of x as we approach from the left of this function f of 4 over what? 4 over x. They're not equal. So it means the limit does not exist. I'll just write TNE. So the limit does not exist. Okay, so that's what we have here. We found that the limit does not exist. All right, let us do the one which follows. So the one which follows is telling us to find the limit the limit as x approaches what? 4. Now here you say, the first thing that we said, you try to put, because it's a rational function. So you put 4 where x is here, you will get 4 minus 4, which is 0. 4 minus 4, which is 0. And we don't want 4 here, the denominator to be equal to what? To be equal to 0. So we don't want it to be equal to 0. And because of that, we are going to what? We are going to, and even here on top, in fact, before I say what I wanted to say, even here on top, when you put 4, you have 4 there minus there inside, you're going to have 3 multiplied by 4 plus 4. This is 12 plus 4, 16. And then you have, for the square root of 16 is just 4. And then you have 0 also. So you are going to have this form. You have 0 over 0, which is an indeterminate form. If you remember your first year, indeterminate what form? Your 1110. Yeah, indeterminate form, which we don't want this here. So it means we have to first simplify our what? Our function here. So what are we going to do? So we are going to what? Rationalize. We're going to rationalize the what? The numerator and the denominator. We're going to multiply by the conjugate, of the numerator. Multiply by the conjugate of the what? Numerator. So this here is going to be this x minus the square root of 3x plus 4 divided by 4 minus x. So the conjugate of the numerator is just x, then that sign changes from negative to positive, and then square root of 3x plus 4. Then there you have x plus the square root of 3x plus 4. And then here, what are we going to get? There on top, you're just going to be getting x squared, and then you have, you're going to have, since you're squaring, so just square that, and then you also square this, and then you keep that negative sign. So here I have minus, and then I square the other side, you get 3x plus what? Plus 4. Yeah. Since these are just conjugates of each other, so I can do that easily. Then down there you have 4 minus x. I'm not going to expand that. I'll leave it like the way it is. 3x plus what? Plus 4. Okay, like this. Then down up here, we can factorize, because there we get a quadratic equation, a quadratic expression, which is x squared minus 3x plus 4. Okay, the fact that I've already done this just factors out to x minus 4. I guess you guys know how to do factorization, x plus 1. Then down there, here I can factor out a negative sign. So it's 4 minus x. So if I factor out a negative, I'll just have x minus what? 4. And then you have x plus square root of 3x plus 4. So we've made these juggles such that this and that there is going to divide. And when they divide, what do we remain with? We just remain with, on top you have x plus 1, and then you have the negative there, and then you have x plus the square root of 3x plus 4, and then I close. Okay, so this is what you're going to what? That you're going to get. Then here, you can substitute the what? That 4 at this stage. You can substitute that 4. So if I substitute the 4, I have 4 plus 1 there, negative sign there, and then you have 4 plus here, when we place 4, we get 12, 12 plus that 4, that gives us what? 16. So you're going to have there on top, you get 5, and then you have 4 plus 4, since the square root of 16 is 4. And then you have 5 over what? 8. So this here is going to be your limit. Of course, I was not writing the limit. So they've given it like this, the limit as x approaches 4, which you could have been writing it here, the limit of x approaches 4, limit of x approaches what? 4, until you replace. That's when you leave it what? You leave it out. I think I just had forgotten that to mention that. But here, oh, the negative sign, we have negative. So negative here, it still follows. Okay. All right. Is there any questions on these limits? All right.
Thank you, sir.
Okay. So let's move on. Next, it's continuity. So we looked at what continuity is, and we're saying no jumps, no breakages. It's just smooth. So here they're telling us, discuss the continuity of the function at the given point of what? Of x. So here we have this function. If then they're telling us if x is not equal to what? -2 at x is equal to what? At x is equal to what? To 2. So we are discussing continuity at x is equal to what? To 2. And then they're telling us that x should not be equal to what? -2. This function x is not going to be equal to -2. Why? Because here you would get a 0. If you get a 0, then it will be what? Discontinuous at that point, because you don't want to get a what? To get a 0. So how are you going to what? To check the continuity here. First, you're going to simplify. Your function is x squared minus 4 plus x plus 2, like this. So this simplifies. There, just the difference of two squares. You have 2x, then x plus 2, and then you have x plus 2 there. So here, u and u can go. You can divide. We have x minus 2 here is going to remain. Then we are looking at, so this here is for x cannot be equal to what? -2. That's what the condition with what we've been given. Now, we evaluate this at x equal to what? To 2. What do we get? So the function at x is equal to 2 is going to be what? It has simplified to this. So where there's x, I put 2 minus 2. This gives me what? 0. Okay, so first of all, it's defined at that point f of x. So now that it's defined at that point f of x, we have to take now the limit. So the limit as x approaches what? 2 of f of x, does it give us 0? Is that question we're going to what? We're going to ask. Does it give us what? 0, as we are going to be approaching what? And it's a linear. So it's simplified. It's the same thing here. That's our function now. Because if you get it here, there, okay, so if you say the limit as x approaches what? Approaches 2, and then you say x squared minus 4. So there, if you plug in your 2 directly, right, you're going to have 2 squared. There, you're going to have 2 plus 2. So there on top, you have 4 minus 4, which is, then you have 4 down there. So that's going to be 0 over 4. 0 over 4 is 0. So the limit exists. The limit is what? Is 0. It's defined at that point. So first of all, we check that, okay, it's defined at this point, and the limit as we approach as we approach 2 of the function f of x is 0. I don't know if that's clear, or maybe let me re-explain. Let me do this. Okay, let's do this here. Okay, so we've said, first of all, it's defined. So the conditions are it must be defined, first of all, at that point. So at the point 2, we've checked, after replacing here, we just got that the function is what? Is 0. Then the limit as x approaches 2 of the function that is x squared minus 4 over x plus 2. So here we do the direct substitution. We have 2 squared minus 4 over 2 plus 2. That is 4 minus 4 over 4, which is 0 over 4, which just gives us 0. So the limit as x approaches 2 of f of x is equal to 0. And the last thing, which is that the limit of x as we approach 2 of f of x, this must be equal to f of what? 2, like that. So in short, it's f of 2 in our case. Yeah, f of 2 there. So this here is the same. 0 is equal to 0. So all the 3 conditions, 1, 2, 3, are satisfied. Hence, our function is continuous at that point of x equal to 2. So you just say, therefore, so you state that since these conditions here are satisfied, since the 3 conditions are satisfied, hence you're going to have that it's going to be continuous at that point, x equal to what? X equal to 2. Okay, so that is how you would discuss continuity here when it comes to such a question. All right, next we have this question. They're telling us to analyze. So we have to analyze, and then analyze how discontinuous supply function, how a discontinuous supply function can affect market equilibrium, and price what? Stability. Then provide an example for your point. So here what we are saying is the discontinuous supply function causes, number 1, sudden jumps in what? In quantity what? Supplied. In quantity supplied. So there are going to be certain jumps. Like from here, you have it that it's showing you that the amount or the price that is there was maybe at 500 kwacha, and then it just jumps to being at 2,000 kwacha. So that is the the point when it's so discontinuous. And remember that function we had, more of like a step function, where here, maybe it's the same part we were saying it's the 500. And then it just jumps to like, they are going this way, it just becomes, maybe there that point is what, 2000. So because there's that discontinuity that maybe is there at this point here, it would mean that it will have those sudden jumps that are going to be there. Then that causes price instability. It means that prices are just going to be like shooting up and down like that. And then what example would we give here? So an example here would be something like when it comes to minimum wage, minimum wage law. So the minimum wage minimum wage law. I think you've worked. We could say these are piece works, where you work for what, for a wage that, or for a small earning that you're going to get. Okay, so now how does this how does this, or what does this law state? So number one, we're saying firms supply labor only above a what, above a legal what, above a legal wage. And then labor supplies jumps what suddenly, then it leads to unemployment or price what, price uh, distortions. So here, these minimum wage laws that like you would see where somebody is paid based on what they have done there. So it's not a fixed salary, for example, no, but then it's today you might be paid based on what you've worked to be 500 kwacha. Maybe the following day, when you come, prices reduce drastically, maybe to 200 kwacha, just like that. So this here, that is an effect of what, having a discontinuous, maybe discontinuous what, function, discontinuous supply what, supply function. Okay, so this here would be something that you would what, that you would give in real life. Okay, this here is gonna be the last question we're gonna look at. So in the context of cost functions, so they're telling us in the context of cost what, cost function, interpret the economic meaning of the limit of this function. So the function f defined at q, or evaluated at q, that is c, q there, then divide q. So they're telling us to find the limit is as we approach q. What does this mean? We should get the interpretation. And then they're telling us where c, q there represents the total what, the total production cost quantity, the total production cost what, cost quantity. So this is a cost a cost what, a cost function. Now let us make sense of this. So in short, they're telling us to find the limit as we approach, as x approaches q of the function. So that function now would be what, would be, that should be x, not q there. It should be x and then divided by what? By x, because you wouldn't have replaced yet. So x like that. So it should be this way. So where this CQ you have said is just the total what? Total cost. This is showing us the total cost. And then our Q is just is what representing, that is quantity. Quantity. Now, what does this interpret to? So if this is your total cost and then you're dividing it by the quantity as in this formula that is there, or that is there, this here just is telling us what the average, what the average cost. That is the average cost that you're going to what to be getting. So now the limit means, what the limit means now as x approaches q there, what that limit means is telling us the average cost when the output is very close to what, to q. Because you don't have to be what, to q, you don't have to be at q exact, but close to q. So it's telling us the average cost when output is what, very close to what, to q. Then also it shows cost what, cost efficiency at what production levels, of at what production level, and that production level is what, based on the quantity q, based on the quantity what, q. But most important, the average what, the average cost is what it's showing us, that as we get closer and closer to q, the average, the limit there is just telling us that that is the average what, this here is the average cost. Okay, so that is what this would mean. I don't know. Is there any question? That is all that we had for today. Do I have any questions?
If it's all that we had today, can you kindly recap on what you just, this question.
Okay, let's do a quick recap on this question. So again, they're telling us in the context of the cost function. So this here is the function. So now remember the function, we said you are generally writing f of x like this. So if it's f of x, meaning this function is f of x is equal to c, where there's q there, there's what? There's x, and then divided by what? Divided by x. So then they're telling us CQ here, when we replace that Q, it represents the what? The total what? Production cost. So in short, it's the total cost that we are having. And then Q is representing the what? The quantity. So it's okay, this is how much total we have, and this is how much we have what? Produced. So now, if this is how much we have produced, then we divide. So here they're dividing then. You see there's over the total cost divided by the quantity that has been produced. So if you divide, what does this essentially mean? So that means that you're getting the average cost. Like what is the average cost for what? For maybe each it can be a good that you're producing. Like what is that average cost that you're having? Now, the limit, the limit does not really get at that point. What we're saying is as we get closer to that point, so in short, as x approaches what? Q, as x gets closer to Q, what does this mean? So this means we are having the average cost, that output here, or this function, since they're telling us interpret the meaning of the limit, this here, which is there, this as x approaches Q. So that is telling us the average cost when we are getting closer to what? Getting closer to Q, that we're going to be having that. And we also did mention to say it shows us the cost, what? The cost efficiency. Or are we efficient as we are getting close to Q, based on how much we have put in and how much we have what? We have produced. On average, what does it usually what? Cost us at the number of quantities, like the number of quantities that we produce. Like if you produce these quantities and then it costs you this, then what is usually your average cost is what the limit as x approaches Q would also interpret. Okay, I don't know if that was heard.
Yes, thank you, sir.
All right, you are welcome. That is it for today. I guess I'll see you in the next class. It's been Dr. Marius, and please share the video with the other people that are not in the group. Add them to the group. It's the whole January, we've just been doing free lessons, and this is topic 2 in your class. So at least you're getting an advantage. We'll do more questions from past papers in the next class, that we understand these limits and just know how to evaluate the limits and the interpretations that we can make out of them. All right, that is it for today, and I'll see you in the next one.